So our speaker today is Sam Daly. Sam got her undergraduate degree, her BA and Bachelor of Engineering from the Thayer School of Engineering here. And then she went on to Caltech, where she got MS and PhD. And then she moved to the University of Michigan as a faculty member, where she's been ever since, and there she's won numerous awards, including having an NSF Career Award and a variety of others. And as of tomorrow, she's actually moving off to California, to the University of California at Santa Barbara. So this is sort of her last talk, I think, as a University of Michigan faculty member to us. So she's going to talk to us today about linking length scales, investigating the effect of microscale strain localization on macroscopic response. So, Sam, thank you.
Thank you, guys, and I thank you truly for inviting me. This is kind of a full circle for me to come back, and it's really an honor, and I'm really delighted to be here. I was last night in the Hanover End just looking over the quad and thinking just how beautiful this place is, and I don't know, what a good education I got here. So thank you for inviting me. So I'm going to be talking today about some work that we have done at the University of Michigan. And I get to come up here and present this work and have all the fun of talking to you guys about it, but this is really my graduate students' work. They're the ones that did all the heavy lifting. They're the ones that spent the hours in the lab. And so the work that I'm talking about today, the development of the microscale scanning electron microscopy work that we do was done by Adam Cammers, and then the application of that methodology to look at phase transformations, that was the work of Mike Kamiecik. So they're really the ones who did a tremendous amount of work on this. Our collaborator is Jay Wayne Jones in the Material Science Department at the University of Michigan, a long-term collaborator who's been very great to work with. I have a co-appointment. My full appointment is in the Department of Mechanical Engineering, but I do have a joint appointment in the Department of Material Science. And I'm at the University of Michigan, but I'm moving to UCSD tomorrow, so I thought it. So, in brief, what my group works on is the interaction between how something is on the kind of micro scale. So we're looking at the microstructure, the constituent level architecture. And these are all things that we work on, and then how this scale and the layup at this scale, or the microstructure at this scale, affects how the material behaves in practical applications. And so there's going to be things like, well, how do things like slip, or twinning, or grain boundary sliding, or damage nucleation and growth, interactions of certain microstructural variations with damage, how do all these things affect the way that a material performs under varied loading conditions? We're particularly interested in loading conditions that are a bit tricky. So we look at, for example, very high cycle fatigue with the Air Force. And in that case, we're looking at TIE 642. And we're looking at how that behaves under fatigue that is very, very low stresses and up to 10 to the 9th cycles. So one of my students is working on this. The reason that we care about that is because the Air Force has vibrating components now, and they're designing components that basically have to last at these very low stresses, and their structural components under gigacycle regime. For those of you who have seen a stress life curve, so you have the stress amplitude and you have the number of cycles, and you come down, right, like this. So basically, on the stress amplitude side, the harder you pull it, the less number of cycles it lasts, right? So if you have a really high stress amplitude, you have a low number of cycles. If you have a lower stress amplitude, so you're not pulling it as hard, it's going to last more cycles. So everybody's familiar with that SN, or that stress life curve. Typically, you see what's called in some metals, you see what's called an endurance limit, which is basically where the stress life curve evens out, and then you say anything under this stress amplitude, if it's really light, the material will last forever, right? Well, that's not true. Nothing lasts forever. And so what happens actually, and the reason that you see these stress life curves out to here, is because you're looking at 10 to the 6, 10 to the 7 cycles, and then usually the data stops. And the reason for that is purely a practical one. If you take a specimen and you test it to 10 to the 9, 10 to the 10 cycles in a typical uniaxial test frame, let's say it can go 5 hertz, you'll be testing one sample for a year. There's no graduate student on Earth who is going to sign up for that project. If you think about how much scatter fatigue has, it has a lot of scatter, right, too. I mean, you look at fatigue data, and it's very scattered, so you need many, many, many specimens. So we were interested in accessing this range, so what we did, and we're interested in, so what happens is the stress life curve comes down like this, and you can use, the kind of the traditional laws over here. When you get to 10 to the 9th cycles, if you go out that far, you'll see a dip again, and you'll see a drop off in how long how long the lifetime is. The mechanism changes. In that very high cycle fatigue regime, above 10 to the 9th cycles, the mechanism becomes microstructural hotspots that cause an initiation of damage and blow out the material. But you have to figure out what those hotspots are because we don't want to process our materials to have those. So how do you access that? So a lot of the stuff that we do, we build these novel methodologies to access regimes that, and make experiments that have not been done before. And so one of the things we did, this is my collaboration with Wayne Jones, we took ultrasonic testing. So there's a limited number of groups in the world that do this ultrasonic testing, where they take a specimen and they put it in ultrasonic resonance at 20 kilohertz, so 20,000 times a second. So you take a carrier specimen, you resonate it at 20,000 times a second, and you attach your specimen on for the ride. And so now you're getting these very low loads, 20,000 times a second. And we needed to examine the effect of microstructure, so we needed to somehow port this inside of a scanning electron microscope so that we could load it at 20,000 times a second while watching the evolution of damage and the evolution of cracks with respect to the grains. So my student was able to, you have this kind of this microstructure, this grain structure. Titanium is a bit tricky in that it has kind of, for those of you who have seen the microstructure, it's got lamella, kind of an alpha beta, and then it has an alpha phase, different phases going on, different structures, almost looks eutectic, like phyllodope. And so we were able to look at the microstructure and then watch cracks coming through. After building, basically we ripped off the door of the SEM and rebuilt a door that was able to port this ultrasonic transducer in. The reason we do that is to look at what type of hotspots do we need to avoid. Where did the cracks nucleate? Why did they nucleate there? Statistically, what type of microstructure will cause cracks to appear and to propagate? And so a lot of our work there, here it's also, we work on lightweighting for structures. This is obviously an automotive structure. It's magnesium, so we're very interested in deformation mechanisms of magnesium as well. We started a project with GE where we are looking at, and this was really fun. So GE is working, and there's a big push in the aerospace industry right now to work on ceramic matrix composites, which are basically, if you had a monolithic ceramic, so you take, here's a piece of aluminum, right, something monolithic, okay? It's going to be very, very strong, but it's going to be very, very brittle. You drop that piece, it's going to shatter. So it's not tough at all, right? In order for something to be tough, it needs to be strong and ductile, right? If you think about the area under the stress strain curve. However, so if you were just looking at, this is a silicon carbide matrix, and this is a silicon carbide fiber. And if you just had the matrix, if you just had the silicon carbide, your material would be very, very strong, but very, very brittle, and it would be useless in a plane. You would not want to fly in a plane with that as a turbine blade, because the minute you had any sort of impact, no turbine blade. But CMCs, or ceramic matrix composites, they can go up to really, really high temperatures, and they're very lightweight. They're beautiful for aerospace applications, but we haven't been able to make them work. And so there's this research thrust on trying to make this work, and they're actually, the LEAP 2 engine just flew with the CMC shroud. And the way that you do it is you have this SiC matrix, and then you have a SiC fiber, and you put a weak boron nitride coating on it. And so now you've got to dissipate energy somehow, right? But you want the ceramic because it's high temperature. So now when a crack comes along, it hits the fiber, and it's either going to deflect up, or it's going to deflect around, and that dissipates energy. So you have many, many, many of these fibers, and you're constantly dissipating energy by the deflection of cracks. So cracking is not bad. These materials are flying now. They've just started flying. Tremendous amount of research investment in these materials right now. And the interesting thing is you actually want these materials to crack. But you want to prevent the bad cracking. You want to prevent the cracking that's going to lead to final catastrophic failure. So you want little micro cracks that basically start, dissipate energy, and then they stop, right? And you want them to be pretty uniformly distributed. So you want to actually control the cracking. So we've been working on that and looking at statistical ways to basically lay out this composite architecture in order to have good cracking and not, I just blew apart my entire component cracking. So things like that. And we look at also, and that work actually is done at, we like to do things in our microscope at kind of unusual conditions. That's actually done at 800 degrees C. You get some interesting things that happen in CNCs at that temperature. So we're doing kind of high temperature loading. But the basic idea is, how do you control things on this length scale to make things better on this length scale? What I'm going to talk about today is some of the experimental methodologies that we use to do that, and I'm going to talk about it in the context of heart stents. So we're going to talk about phase transformations in a material that's called nickel titanium, which is used in heart stents, and we're going to talk about kind of how we control those phase transformations. So I talked a little bit about this on the last slide, but some of the questions that come up when you're trying to connect how do you process a material, how do you make a material, whether you're laying up a composite or whether you're trying to process grains and have a certain texture to them. When you're assessing damage in material, what length scale do you look at? Do you do a test and look at the millimeter scale? Do you go down and look at TEM to look at damage on a nanoscale? Do you use an F? What machines do you look at to try to assess how the damage is progressing in the material? What are the critical length scales? We spend a lot of time looking at the microstructure. What are the microstructural triggers? What is it about the way the composite's laid up? What is it about the way that your grains are oriented that will create localized damage that are your little hot spots that later blow out your component? And how do you avoid those? If you're GE and you're laying up a composite, you're laying up that ceramic matrix composite for use in a turbine blade, you have, practically speaking, you have a certain amount of money and you have a certain amount of time. What do you spend that on? Do you spend that money on time on making sure that your fibers are a certain diameter? Do you spend that money on making sure they're uniformly distributed? Do you spend that money on making sure that they have a thickness coating that's less than 20 nanometers? What's important? And how do you make the best material given certain processing bounds? And what is the kind of sensitivity to those processing bounds, right? Is it okay if the fiber coating is less than 50 nanometers? Is that important at all? So we do a lot of statistical measures to look at basically like, what is your bang for the buck in terms of how you can make better materials? And then certain aspects of damage, like this cracking in the CNCs, that you either want to suppress or promote. Damage is not bad. Materials dissipate energy sometimes by getting damaged. Damage is going to happen. But you want to control that damage to prolong the life of the material. So we have two kind of focuses in our group, foci. One is developing new testing methodologies to try to provide, like the very high cycle fatigue in the SEM, to try to provide information about these spatially distributed damage mechanisms at the microscale. We like working at the microscale because you can kind of reach down to the atomistic scale and you can kind of reach up to the macroscale, so we found it very convenient in order to link length scales. And then what basically happens, and I'll talk about this, this is very new work on our end, is we ended up developing this experimental approach that's giving us very, very large data sets. And then the question is, okay, how do you handle these data sets? So we're taking some machine learning, some self-organized mapping approaches to try to handle all this large data that's coming out of our approach. This is something that many people in our community are facing right now, the mechanics and materials community. If you look at the data that's coming out of experiments now, if you go to the synchrotron, right? So the synchrotron is a big ring that basically spins electrons, and you pull them out and basically shoot them through a material and look at how they diffract. You get a tremendous amount of data. TEM, you get a tremendous amount of data. It's the Auger, I mean, just these experimental techniques that we're coming up with are giving us more and more and more data. And it's almost like taking pictures with your iPhone, where 20 years ago you go on a trip and you take 20 photos, and they may not be the best photos, but you could really look at them and put them in frames. And now you go with your iPhone and you take 2,000 pictures of your trip, and you don't look at all the pictures, right? So machine learning is a way to kind of, and you can't look at all the pictures, and you can't go through all of them. Machine learning is kind of a way to sort through those images, that data, and to pull out what you should be looking at. And so there's kind of this push for integrated computational material science engineering, this push for looking at larger data sets and how to handle those types of information. So that's what we focus on. And the material that I'm going to use as a model material to talk about these types of approaches that we're doing today are these shape memory alloys. So shape memory alloys are really cool. They have two unique properties. One is that they can remember a previously defined shape when you deform and then heat them. So you can actually take a material and you can wire this and you can bend it, let go, heat it, and it will go back to its original shape. So that's where the shape memory comes from. It does this through phase transformation. They're also super elastic. These happen by different paths. I'm actually going to focus, because of time, this is dead, on the superelasticity. The superelasticity is basically exactly what it sounds like. The stents are almost like Gumby metals, where you can bend them and twist them and they'll pop right back. So I'm going to show you a video. And we work on, there's a bunch of different ones. We work on nickel titanium, which is a nearly equiatomic mix of nickel and titanium atoms. So if you look here, you're going to see them poking the stents and bending them. They go by the trade name nitinol. The great thing about these stents, and there's also like heart patches made out of this material, there's a bunch of different biomedical devices, is that they're very non-intrusive to get into the body. So instead of having, like if you had a stainless steel stent, you basically have to cut somebody open and go in and put the stainless steel stent in and then sew them back up, because if you squish the stainless steel stent, it won't come back. These stents come back. So one of my friends actually had this put in. She had, oh, it's right here. Great. Okay, so this one right here. With permission, this is a picture of my friend's heart from grad school. She was having strokes. It ended up that she had a hole in her heart, a PFO. And so you can see here's the heart wall. And this is what's called an Amplatzer septal defect occlusion device. Amplatzer is the brand. Septal defect just means a heart defect. Occlusion means you're blocking it, so you don't have any more strokes. And so what they did, you can see the heart wall right here, and this is one half of the heart patch, and this is the other, and it's basically just closing up the hole. So this is made up of this nickel titanium. And because you could take those two pieces, and you can see the catheter coming down here. So they pulled those two sides of the heart patch into the catheter. So you just had this very long wire. And they cut a 1-inch hole in her leg, and they wove it up through her femoral artery up into her heart. And then they basically deployed it inside her heart. So they pulled the sheath off the catheter, and out came, they poked through the hole in the heart, they pulled the sheet off the catheter, out comes the first side. They pull the other sheath off the catheter, out comes the second, and they glue it together, and they remove the catheter. So instead of being in the hospital for a week, she was in the hospital for one night, and she had a 1-inch hole in her leg, and that was 15 years ago, and it's been beautiful. It's been wonderful. So this is a really great material, and whether it's going to be a stent or whether it's going to be a heart patch or anything like that, it's a great way to get medical devices in the body in a way that reduces mortality, reduces time in the hospital, and reduces how much you have to rip apart to get in there. So superelasticity is very useful property. And so you can see there on the bottom, kind of like that's the tube being pulled off of the stent that's being deployed out of the tube. The same idea that you're squishing it down. The reason you can squish it down and do this and deploy inside the body is because superelastic nitinol goes through a phase transformation. So you can see you can put very, very large strains on it. It's a weird stress strain curve. And you can recover all those strains. So you can really crank it down and release it, and it'll come back. What's happening when you do that is that the material is going through a phase transformation. So the material starts out, this is some data from one of our experiments. And I'll explain how we get this. The material down here starts out in a B2 cubic. So it's basically a B2 cubic. We call it austenite. I'm using these words a lot. And you basically kind of load the austenite pretty elastically. And then at some point right here, this is actually, from our data, this is a thin strip, maybe an inch-long strip of nickel titanium that we just pulled. What's going to happen is the purple, this is strain. The purple is really low strain, 0%, 0.5%, somewhere along there. The yellow is high strain, that's about 6%. And what's happening is when you pull this little strip, as you're going along the stress strain curve, you get martensite that nucleates. Martensite, so the austenite is a B2 cubic, and the martensite phase is kind of like it's called a tetragon. It's called a B19 monoclinic. It's a monoclinic. It's basically a tetragon that's skewed. So you've gone from, it's a displacive transformation, so you're not doing any diffusion. All you're doing is the atoms are going like this and like that. Now you can imagine there's actually different variants of martensite. If you're going cubic to tetragonal, that tetragon could happen in a couple different ways, right? So let's say you're going from cubic to tetragonal. You could either go like this, or you could go like this, or you could go like this, right? Okay, or this. Those are all equivalently the same. They're energetically the same. Those are called variants of martensite. So we'll come back to that. But here you start in the B2 cubic austenite. You load up. You pull your sheet. This purple is the low strain. This is the austenite. And this yellow is the martensite that nucleates. And it's almost like a Luther's band. It propagates through the material in a very highly localized strain pattern. So here you've got 0% strain. Here you've got like 6% strain. This is cubic. That's monoclinic. Okay, some variant of the martensite. Okay. There's actually 12 variants of monoclinic that are energetically the same. Okay? And it propagates through until you're here. And then you're basically elastically loading the austenite. And now when you release, You come back down and you start the reverse transformation from martensite back to austenite. This plateau, this is what gives you all that recoverable strain. So that phase transformation, that localized Lüders-like phase transformation, is what gives you all the recoverable strain that lets you squish these stents and these hard defect occluders. So you get it through this phase transformation. Now there's a lot of interesting stuff, and one of the reasons we like working on nitinol is because it's so interesting on so many different length scales. So it's a perfect model material to start to develop these approaches and to develop the way that we look at multiple interactions happening at different length scales. So you can imagine at the very small length scale, remember I talked about those variants? You could either have a tetragon like this or like this. So here's one variant, it's a tetragon like that. Here's another, here's another, here's another, right? So you've got two variants that are matching. Okay? So you can have variants that are twinning. And those variants can exist in a little tiny band of martensite that can form what's called a habit plane with the austenite. So this is the monoclinic, this is the cubic, another martensite. Those are going to form another habit plane with more austenite and martensite. That can be inside of a grain where some of the grain is transforming and some of it isn't. Turns out that transformation in grains can be very heterogeneous, where some of the atoms can actually transform to the monoclinic and some just stay as a cubic. And so that'll change the stress state in the grain. So you're loading, and that changes the stress state in the grain, and that changes the transformation in the grains all around it. And then the mesoscale, you have basically the localized Lüders bands that are propagating, right, the spatial scale, and propagating through the material. And then on the macroscale, you've got this really weird stress strain curve showing the hysteretic behavior. So there's a lot of stuff going on in this material at different length scales. The great thing about this material, too, is that there's a lot of, as we're developing these things, there's a lot of symmetry relations that we can use to understand what's being formed and how it's interacting with its environment, its local environment around it. So one of the ways that we can quantify strain, and we take strain to be, you guys saw in the picture where the austenite was like a 0% strain and the martensite was a 6% strain. So strain is a huge indicator of transformation in these materials. And an indicator of the extent of transformation. We can actually associate a transformation strain. And so one of the ways that we look at this is we use something called digital image correlation. And what this is, it's kind of like a next-gen strain gauge. So what you do is you can imagine if you had a specimen, okay, and you put 2 dots on it, and you pull it, and you track those 2 dots, it would act as an extensometer, right? So we do that, except we paint the specimen with many, many, many dots. And so we have the specimen, we paint it with a random isotropic assortment of dots, and we draw a box, a subset. And we try to keep the same dots in that subset when we pull the box. So, it starts out square, and then as you pull and you continue to take images through the test, the box is going to change its shape. And you do that for many, many boxes that are overlapping, and you minimize some cross-correlation functions, and you can get a very, very accurate full-field strain on the surface of the specimen. And so if you do 2D, that's one image and one specimen and one camera on the specimen. The problem with 2D is everything has to be planar, because the minute that you move your specimen towards the camera, if I do this, the dots look bigger, but I haven't actually applied any strain to the camera, right? When we've done a rigid body displacement. So you have to be very careful about 2D, keeping things in plane. If you do 3D DIC, you actually have 2 cameras on the specimen, and you can do kind of these out-of-plane displacements. So we started out this work on the macro scale. So we were looking at this material, we were looking at it in the context of stents, and we had this setup. We have 2 cameras because we're doing 3D DIC, and we have an infrared camera because this is actually a first-order phase transformation where latent heat and the extended transformation will strain interconnect. And we have a specimen, we have a laser extensometer just for a sanity check, and we have a specimen thermocouple also for a sanity check. The whole thing's draped in netting to keep the temperature a little bit more consistent. And then we have an ambient thermocouple, so we know our lab actually changes a fair amount of temperature, so that we know what's going on. And we take these little sheets. Stents are actually cut from tubes. We take this little sheet and we pull it. And so you start out in this austenite, and you're tracking all these dots with relation to each other. There goes the martensite. I mean, it's a really sharp band. And it comes up, so that's 6% strain, and the purple's 1% strain. Hugely localized strains. And then when you release, it comes back with nearly perfect recovery. So then the question was, okay, well, how does this change recycling? We know, and we actually picked a material that had a huge change in cycling because we wanted to make it really obvious. So here's the nickel tie material, and we looked at it from cycle 1 to cycle 50. Each one of these dots is an image that has 500,000 strain values that you saw before, that are all averaged to produce one strain value and then plotted versus the applied stress. Okay? So each one of these dots represents an image. And you can see that when you're cycling, you really change macroscopically a lot what you're doing. Not so much on the back end, but very much on the front end. So as you're cycling, it becomes easier to nucleate transformation, and it kind of doesn't last as long. You start to get some additional stuff going on. So, okay, so macroscopically things change a lot. And we took images at the midpoint of transformation for cycles 1 through 50. And when you look at those, what we saw was that there seemed to be a lot of similarity straight off the bat. So we just started noticing this, and we said, okay, look, you've got, and some things flip around. This flipped like mid-cycle, but you've got a lot of similarity here. It's just something visually that we saw. And then we quantified it. So the martensite we saw was forming very similarly from cycle to cycle. This is important because it means that if you can control how the martensite forms on the first cycle, you can control how it's going to form on the 10,000th cycle if it's got a lot of similarity. So we wanted to quantify how much similarity there was. One of the first things we looked at, we did a pretty simple experiment. We wanted to see what microstructure's effect on this transformation similarity was. So we took a sheet and we just cut out specimens in 3 directions. We cut them out in the rolling direction, in the 45 direction, and in the transverse direction. And Miyazaki had done some work in 2000, and it's used a lot in mean field theories, where he said that when you have a grain, the variant that nucleates in that grain will be the most favorable one. Remember the variance? It'll be the most favorable one, and it'll subsume the entire grain. This is the model that's being used in most mean field theories. However, most mean field theories aren't very good at predicting fatigue of these components, and it's a problem. So we were curious how accurate this model is. To start off, we said, okay, well, we first want to know, like, how good are these, using that theory, how good are these different specimens that we've cut out going to be? So we took XRD data on them. So this is our RD, 45, and TD. We're up here. And looking at this, you can see here, this is the transformation strain. So that's basically how long the plateau is. So the longer the plateau is, kind of the better, the more strain you can get, the more bendy the material is. That's the way to think about it. Okay? You get more bang for your buck from the transformation. And if you have kind of texture here or texture here, you have very large transformations. Down here, things don't go so well. So the TD in there, the TD is not great. The 45 and the RD are actually pretty good for transformation. Okay, and that's what we saw when we tested these. So, and that's actually fairly well known. But we wanted to make sure that our material was doing what it should. So this is the 45 and the RD, and you can see that it doesn't take much stress to introduce transformation, and you get a lot of transformation. So those are pretty good. The transverse one, the one we cut like this, you have to pull really hard to get it to transform, and it ends really quickly. And so, so the experiment matched with what we expected from the texture measurements, and the transverse direction is going to be less favorable for transformation. But what does that mean for the similarity? Well, it turns out that if you have an unfavorable transformation texture, if you cut your stent perpendicular to the rolling direction of the sheet, you will get less squishiness, you'll get less superelasticity, but you'll have more predictability. You'll have more transformation similarity from cycle to cycle. So it's kind of a trade-off. You can get a stent that performs not as well, but you can predict it better. But why? Why would that happen? Why does having a worse, what is it about the grain structure that having a worse transformation characteristic actually makes it better in terms of from cycle to cycle predictability? And so we said, well, we really want to look at this. So why does poor texture cause more transformation memory? What is it about that? And one of the things, some of the things that we knew, the macroscopic response depends heavily on the microstructure. That's known. So here, if you look, remember this is the RD, this is the TD. You change the microstructure, you drastically change the performance of this material. There was some experiment that had just come out that indicated that this idea that Miyazaki had, that you have one variant that subsumes the entire grain, that wasn't right. And so there were some qualitative experiments that had come out with filtered microscopy that seemed to show that there were areas of the grain that were transforming more than others. So that was just starting to come out. And then we found this really strong cyclic transformation memory for the first time that kind of showed that there had to be some sort of really specific microstructural constraints on transformation. There was something that was driving it to transform the same way over and over. And what we think is happening is that the first time you transform, you lay down a dislocation network, you lay down Martin-Stick variants that get locked in, and it's almost like a net of things that don't change, and then you have to work within that net, and so you get similarity that happens. But we really wanted to see what was going on the microstructural level. So if you remember this DIC technique, one of the cool things about this DIC technique is it's not length scale dependent. It's length scale independent. When you correlate these two images and you calculate the strain, the correlation algorithm doesn't care if you've done this on an AFM image or if you've done this on a bridge, right? It doesn't care. It is simply correlating dots. So this is completely length scale independent. If you can get an undistorted image with the right pattern of dots, you can do this at any length scale. So when I first started, like 2 or 3 years into being a professor, I was kind of like, okay, we'll go do this, and like a little naive, and because it ended up being really hard. I had a really great student, Adam, who did this, and so I said, okay, we're going to do this inside a scanning electron microscope. So we just need to figure out a way to pattern this and correct for some of the distortions, and we'll be able to get these strain fields. We built this off of some ideas and framework fortunately from Helena Jin and Mike Sutton. And so the first thing we had to figure out was, how do you pattern something? If you're looking inside, we basically wanted the equivalent of dropping like 500,000 strain gauges inside a 10-micron field of view. For reference, if you take a penny and you flip a penny over and you find the Lincoln Monument, and then you go find Abe Lincoln inside that monument, and then you go find his legs, okay? His legs are about 100 microns in width. That's about the resolvable limit of the human eye. We're trying to use this methodology to drop the equivalent of 500,000 strain gauges inside 1/10 the diameter of Abe Lincoln's leg on the back of the penny. So we had to figure out a way to pattern a very, very, very small area that you can't even see with the naked eye, and to make it look like this. So, and we ended up doing this from about 10 micron field of view up to about 300 micron field of view. It's about where we were. So when we first started, we had a bunch of stuff we tried. We tried like depositing chemical vapor and lifting it off. We tried blowing gold through TEM grids. We tried all sorts of stuff. One of the first things we tried was actually E-beam lithography, which is the deposition technique. And the problem with that, this is right here. So if you're up at the macro scale, you can just airbrush it, and you can airbrush it anything about 1 millimeter or more. You can just use an airbrush, like when you do with shirts, right? When you're painting shirts, that type of airbrush. We tried next actually doing E-beam lithography. The problem with that is, A, the image isn't very good. This actually isn't very random, and you need something that's very, very random in order to make the boxes, the grayscale in the boxes, unique enough for tracking. The second problem was it was incredibly expensive. The fab fees on that were, $1,000 for a sample every time we do it. That's not, you can't do that. And the third problem was actually that you needed a completely flat surface. And we wanted to look at CMCs, which weren't as flat. They were flat. They weren't as flat as we needed. We also wanted to look at crack propagation at the time in CMCs. And if you don't know where the crack's going to go, and you have to use E-beam to pattern everywhere around the sample, it's now a $10,000 sample, right? It's just not feasible. And the pattern wasn't good. So then we tried drop casting nanoparticles. So we were drop casting them and basically taking nanoparticles in solution and spinning them. And the problem with that was this is totally cherry-picked. So what happens when you drop cast nanoparticles on a specimen is they immediately coffee ring. Just like when you put your coffee down on the table, you'll form like a ring. So there's areas where, yeah, the density is great for deformation tracking, but you'd have to go around and cherry-pick the area, and everywhere else would not be very good. We're trying to look at fracture. We're A, trying to look at like crack paths, and B, we're trying to get enough information that we can do many, many, many fields of view and pull out statistical correlations. We need the pattern not to just be okay in one spot. We need to be able to control it and have it be okay everywhere. So I was running with my friend, and I was talking to her about this, and we were running around the track because it was winter. And I was like, God, there's only some way that I could get the nanoparticles to stick. So we were talking about this and trying to figure it out. And I stepped in gum. I thought, and I was like, oh man, right? So but then I realized, like, if there was a chemical gum that we could put on the nanoparticles to make them stick, we could solve our problem. So I got to go back to my student and do the easy part of saying, let's find a chemical gum. And so what we did was we created a silanization procedure. This is not cherry-picked. We created a way that we can chemically silanize our chemically functionalize our specimen. We take the specimen, we dip it in a batch of chemicals. What ends up happening is that you get pendant functional groups on the surface. So they look like, so you drop it in the chemistry. You get these little, they're almost like little functional groups on the surface that coat the entire surface. And then when you drop your nanoparticles in, each little group grabs one nanoparticle, and you have this beautifully uniform spread of nanoparticles on the surface that we can track. And when we're done, we can just chemically break the bonds and get rid of them for Ebsd. So we figured this chemistry out, and we were at the time we're buying nanoparticles from Ted Peller for like $100 a little vial. Again, not feasible. So we actually now make our own nanoparticles. There was a procedure that was published by friends in about 1972 that you can buy them. You can build your own nanoparticles for about $2 a bucket, which is great. And the reason that that's fantastic for us is also because we can actually change the chemistry of the nanoparticle formation to get nanoparticles the size we want, so we can tune them to exactly the field of view that we want to investigate. There's a certain size of speckle or dot that you're tracking that will give you the highest resolution, and because we're doing statistical correlations on these deformations, we need really high resolution. If we can build our own nanoparticles, if we can control them, then we can pick whatever field of view we want. And we can spread them over the entire surface, and then we can get multiple fields of view with multiple deformations in them and pull out statistically significant results. So it was very important to us that we were able to build our own as well and distribute them uniformly. So that was the first challenge. We got over that hump. The next problem was actually distortions in the scanning electron microscope. So if you're doing this approach and you're doing it on the macro scale, you take your specimen, you take a camera, and you take images. Boom, boom, boom. And all the pixels are taken at the same time. You take an image, you collect everything at the same time. There's going to be a parametric distortion to your lens, right? Just like your glasses lens. Like if you look through the center of your glasses, it's not distorted. But if you look off to the side, there's a distortion, right? It's the same in a camera lens. That's very easy to correct for. It's very parametric. You can establish it and correct for it, and it doesn't really change. When you're in an SEM is a scanning electron microscope. So the issue with this is that A, you're not collecting every point at the same time, and B, you still have lens distortions, except they're different. So every lens has a distortion in it. Whether it's bending light or whether it's bending electrons, it's still going to have a defect. There's no perfect lens. The problem is that when you have an optical lens, it is pretty much a parametric distortion. When you have an electron lens that's bending electrons, it's going to depend on a bunch of factors like the alignment of the system that you have to account for every time you do the experiments. And it's not going to be this pretty parametric. It's going to be something different every time. So there's two different distortions that we had to work with. One was the spatial distortion, which is just due to the fact that you have these lenses. They're not perfect. They're bending the electrons. If you guys are ever on an SEM, you can see it. Pull your SEM all the way out to a big field of view, and you'll see your specimen start to work. You can visually see it. It's because you're trying to bend the electrons so far that they start to work, the specimen image. So the spatial distortion will kill you at big fields of view. Anything about 300 microns or more, you can really start to see some warping. Pull it out to a millimeter, you'll totally see it. The drift distortion is a little bit different. So the drift distortion is the fact that you're actually, once you set the spatial distortion, this is a lens thing, you set it at the beginning of your test, you're done. The drift distortion is trickier. This is time dependent. So what basically happens is that in a theoretical scan, this is your image, you would dwell at the same time at every single point. You'd have a very well-behaved jump to the next line, you have a very well-behaved jump to the next line. That's totally not what happens in an SEM. You can dwell for longer times, and then you can dwell for really short times, and then you can have a short jump and then a long jump, and this will change from image to image. So if you're trying to compare two images, and you took the images at this first one, like here, and then the second time you do it, your data points have shifted, you can't compare those. Your image will tell you that these are XY, and then it'll tell you that these are XY, but they're actually have moved because the beam has drifted. So you need to correct for those as well. So they're significant distortions, and if you want to get statistically significant correlations, you have to correct for them. I'm going to skip through this just due to time, but if you're interested, please come up and talk to me afterwards. It took us a while to figure out, but we were able to actually correct for these distortions. So this is an example where we took a specimen and we moved it 300 microns to the right, so 3 of Abe Lincoln's legs to the right. And every point in that image should move, it's a rigid translation, should move 300 microns to the right. But if you look, this point is moving like 296. This point's moving 304. So what's really happening is, even though you're doing this, the image is telling you because of this beam drift and because of this spatial drift, the image is telling you that your specimen is actually straining when it's not. However, when you correct for these distortions, and there's multiple splines and time-varying splines you have to do, you actually get that every point in the specimen is moving 300 microns to the right. So that's good. So we can trust our deformation points. There's also, the fact that you have data noise in an SEM. So there's inherent noise. When you take an image in the SEM, it looks very pretty, and you take a fly, you gold coat it, but you don't care as much about these really little noise issues. But when you're trying to get statistically significant measures of deformation, you do. This is a typical noise profile of an optical camera, a really high quality 5 megapixel optical camera. And this is a typical noise profile of a SEM that's been pretty well matched. These are reasonable settings that you would choose. In general, you can use a longer dwell time, you can average scans, and you can increase the spot size. However, nothing comes without a price. If you use a longer dwell time, you're spending longer on your scan. You can induce more damage, you can induce more contamination, which can induce more drift, you can have stress relaxation, all sorts of things. So it's a balance. Doing a noise parameterization study is important for any type of characterization in the SEM. And the only thing I want to show you here is, in general, yes, longer dwell time, average scans, increased spot size. However, spending a really long time getting your image in an SEM doesn't mean that you're going to have a better image. You could spend 360 seconds getting an image, and you would get that noise. You could spend 18 seconds getting an image, and you would have this noise. Okay, so longer time doesn't always equate to a better image. Okay, so now we're going to use this approach to look at this multiscale phase transformation and look at it at the microstructural length scale. So this is looking end-on in our stage, and here we have the specimen, and we basically pulled out the SEM. So the SEM's up here, and we pulled it out, and here's our specimen load stage, and we're putting it in, and then we're just going to push this in. And this is what it looks like, not to scale, but here's our load frame. So we're coming on the side of the test skin now, our SEM. And here's our specimen. Here's a little field of view. And we have actually little platinum markers here that marks because otherwise we wouldn't be able to find our field of view again. So we need some sort of scouting system. This is an Ebsd pattern. What this tells us, Ebsd stands for electron backscatter diffraction. You basically take a specimen, you shoot electrons at it, it penetrates the first 200 nanometers, and then you have another detector, you watch how they bounce off, and it'll tell you how the atoms are arranged in a grain. You can imagine if your atoms were like this, you'd bounce here, and you'd bounce here. And you can measure that and figure out, right? Versus if you're like this, and your atoms, let's say it's a cube, and you're in this grain, they will bounce differently. So you can measure that spacing, which are called Kikuchi bands, and you can figure out how your atoms are arranged in a grain. Each one of these colors is a different grain. So maybe in the green, your cube's arranged like this. Maybe in the blue, your cube's arranged like this. Maybe in the purple, your cube's arranged like this. Same phase, all cubic, different orientation that you get from measuring these backscattered electrons. So electron, backscatter, diffraction. Ebsd. Okay. So when we use this approach and we look at, remember that big, we pulled the material and we had that big band coming through? You're going to see that band come through this field of view. This is 200 microns in width, and you can see all the grain boundaries in white. And you can see our little scouting markers right here from our fib deposition. Fib is focused ion beam. It's like a really, really small mill. You can mill out. You can also deposit things in the SEM. We deposited platinum so that we would know where to find our field of view again. So we're pulling, and okay, so this is the first thing off the bat. The kind of conventional thing about this phase transformation was that there was a very sharp interface. And right off the bat, we didn't see this. So these are, as far as we know, the first direct observations of what happens to phase transformation on the microscale as it progresses through grains, across a wide view of grains. There have been TEM studies, but there hasn't been this length scale. And so people thought that there was a very sharp interface. And right off the bat, we see a very crosshatched interface. It's very diffuse. And when you come through, okay, this is the other thing. So remember how Miyazaki said that when you have a grain of a certain orientation, a specific variant will nucleate and it'll take over the whole grain? Whichever variant is the most favorable will take over the whole grain. That's totally not, and this is used in theories all the time right now, totally not true. If you look at these grains, this is very heterogeneous. There are regions in this microstructure where there are grains, right here, where you've got a ton of transformation up here and nothing happening over here. So you've actually changed. There's part of the grain that's in cubic, and there's part of the grain that's not. Okay, so this assumption is not correct. And then when you release, you can see it recede with very little deformation. Okay, so that's that plateau that's coming back. Okay, that's that squishing of the stent and release. And so right away, we were able to see with this new methodology, we were able to see a lot of immediate observations. One was that it was very heterogeneous. This idea of a single variant subsuming a grain, not true. You have grains that can accommodate both a very heavily deformed martensite phase and an austenite phase. There is an argument in the community right now about transformation progresses contiguously. Like you have a grain that transforms, another one transforms, another one transforms, almost like pebbles rolling down a hill. That's not true. We actually saw transformation that would skip over grains. It would proceed in kind of a disordered manner. The martensite front is microstructurally diffuse, and instead of getting like a sharp transformation front, you get this crosshatch pattern that's coming through. We're trying to resist damage in these materials. We're trying to make better stents. And so we're trying to resist plasticity. Plasticity also is bad because it appears that when you have plasticity, it interferes with reverse transformation too. It just builds on itself. And this idea of the strain fields with the grain. Okay, so back to that similarity. You guys remember when we were pulling a specimen and we were seeing the same type of microstructure of the martensite form over and over again, right? But now let's look at it at the grain level. So this is the maximum strain in this tiny little field of view, 200 microns. And in cycle 1, I'm going to flip through over here in cycle 2, 3, and 4, and 2, 3, 4, and 5 maybe. And what you're going to see is it's almost like I took the image and just shifted it around a little bit. The shifting is just due to the fact that if you think about it, we have this specimen in a stage. We do our best to keep it centered, but there's going to be some natural shifting of the specimen as we load and unload. But what's really crazy is, the pattern is so faithful, right? You look at this. This literally looks like I took it and just shifted it around, but these are actually load and unload cycles, and it's forming the exact same way every time. Very, very similar, right? So there's a very strong dislocation network that lays down. There's a very strong network of, we think, residual martensite that's laying down that's causing this to form in the exact same way over and over again, very faithfully. And so one of the questions that we were able to look at right away was this assumption that's used in modeling that similarly oriented grains transform similarly. If you have two grains that are both cubic, that are both oriented like this, regardless of their surroundings, the idea is that they will transform the same way. They will have the same amount of transformation. We were able to actually disprove that pretty quickly once we had this data. You take three grains that are similarly oriented, and you look at basically strain as an extent of transformation. Here you have a lot of strain, right? Lots of transformation. And not a very wide range. So this black bar, this thick black bar, is 50%, and then the thin is like 99%. So all of the 5,000 data points in each grain, each 5-micron grain has about 5,000 data points in it. Of those data points, 50% of them fall within this strain range, and 99% of them fall within this strain range. So we've got the equivalent of dropping like 5,000 data points inside of each grain. And so this grain is very high strain, and not a very wide range. These are all super similarly oriented. This one has kind of the same strain range, but much lower strain, much lower overall transformation. This one has the same overall transformation, but it's much more heterogeneous, right? You've got a much higher strain range. So not only do they not transform similarly, these grains are all pretty much oriented the same way, they don't transform similarly in the amount that they're transforming, and they don't transform similarly in the distribution of how they're transforming in either metric. Those are only three grains. So what happens if we take let's say, all the grains in the field of view, each one containing about 5,000 strain data points, and we just plot ones that are less than 5 degrees misoriented from each other. So we picked the sample axis just to have a reference point. And any grain that was oriented less than 5 degrees from the sample axis, we plotted. Where the thick part is the 50% of those 5,000 data points fall in that strain. The thin part is 99%. And the color is how big the grain is, because maybe the size of the grain matters. And it turns out, it's all over the map. You can't predict. It's not reasonable to predict in modeling how much a grain is going to transform by having similar orientations, and you do have to consider the neighborhood. Here, you have very similar grain size. They're all blue. You have incredibly similar orientation, right? They're all within this tiny little, angle of difference from each other. So they're the same size. They're all pretty much dark blue. They're the same as orientation. They're all pretty much exactly the same type of grain, and they're totally different from each other. You've got one guy down here who's got basically no transformation and a tremendous amount of heterogeneity. So maybe he has a grain with like a tremendous amount of strain on this side, some transformation on this side. You've got another grain up here who's totally having a party all by himself. He's got all sorts of transformation going on. He's fully transformed. And so there's no real pattern to it. So then the question was, okay, so these grains are transforming all differently. If we're trying to prevent damage in these materials, why does damage form in some locations and not others? And we pulled out just grains that had substantial amount of damage, and we just looked, I only plotted 6 here, but we pulled out about 2,000. And we just looked to see if there was any clear correlation to grain size, grain orientation, and there wasn't. And we didn't expect to find one, but we should check. So it turns out that there's no, when you look at this right off the bat, there's no, 80% of the grains that had significant damage were over a grain size of 5 microns. There's nothing like that popped up. It's very dependent on the local neighborhood. So we had to figure out, and there was subgrain damage, what was basically causing the damage, if it was reversible, if it wasn't, and what were the mechanisms that were happening inside a grain. So this is a grain that I'm just going to show you, and I'm going to be brief about this part of it because I want to get to the machine learning part. But we picked a grain that had about 3,000 strain values in it, and we looked at strain as an extent of transformation. And to convince you that we can actually pull out the exact mechanisms of what's happening inside of each grain, what we basically did, I'm going to go over just a brief terminology, is look at these different correspondent variants. Everything's symmetry related. So the purple side are the different correspondent variants. So maybe this light purple is this tetragon, and the dark purple is this tetragon, and that's their twin, like we showed before. So you've got one correspondent variant, one tetragon up here, and it's twinning with another one. Those twins form kind of a layer cake that will, these are all the martensites, right? So the tetragons, that will form a plane with the cubic austenite. So over here you've got, on the layer cake side, you've got tetragon, 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 and it's forming an interface with the cubic austenite. You've got to have a very specific mixture in order to do that, just by symmetry relations. Okay? So you can calculate that mixture. And this is called a habit plane variant, the big one. So if you take all these data points inside a grain and you throw them into strain space, they actually cluster around certain shapes. They actually cluster along a tetragon. And the reason they do that is because they all relate back to a specific type of variant that introduces a specific type of strain. So you can imagine you take a strain data point and you plot it here. This is 0 strain. So this would be nothing's happening. You don't have any change from the austenite. The austenite is the reference. So you're fully austenite here. This would be, I'm 100% whatever that HPV is. The HPV is the purple layer cake. So that's going to give you a certain strain. You can calculate that. And then anything along here would be some combination of those two correspondent variants. You have 12 of these possibilities. You have 12 possible correspondent variants, and you have any possible mixture of them in layer cake form with the austenite. But you can plot all of that. You can imagine in strain space these interlocking tetrahedra. And it ends up being just a bunch of tetrahedra. When you plot all the strain points in a grain, they all cluster around a certain tetrahedra, and that tells you what correspondent variant is active. So you can actually say exactly this correspondent variant is active with a pretty high degree of certainty. You can have 2 variant pairs, which are then going to be distance to a plane. So you can have, you imagine this habit plane variant where you have the layer cake with the austenite. You can actually have 2 different types of those. You can have another habit plane variant that's a different symmetry, again with the austenite. The spatial scale of our data will allow that. And then it would be distance to a plane. So we're able to plot this, and we're able to determine, if we had this mechanism, you plot all the strain data points, you find the mechanism that's active, and then you predict what strain that mechanism would give you. And when you do, the match is terrible. It sucks. And the problem is, so it didn't work at all. We weren't able to match. This is the theoretical, by saying that it has to be these tetragons, and this is the experimental. And we had really, really high strains in the experimental that we simply weren't able to match by any combination of correspondent variants. We just couldn't get them to work. We could match the low strain regions really well, but we couldn't get the high. People had said for a long time that detwinning didn't happen until the end of the stress plateau. What detwinning is, and we hadn't considered it, because it was kind of common knowledge that it didn't happen. We had used the modeling that didn't happen before the end of the stress plateau. What detwinning is when you break the symmetry of the tetragon twins. So remember I said the tetragons have to be in a certain proportion in order to make the habit plane with the cubic work, right, with lowest energy. If you break that and you let one of the layers grow in cost of the other, you cause an energy cost here. It happens when you apply a lot of deformation at the end of the cycle, and you apply a lot of, it has to accommodate it somehow. Well, it turns out that if you allow this detwinning to happen, so you do the same type of plotting, but now you say, we moved it to a transformation space. I won't go into that, but you basically are plotting the strains. And you now allow two of these possible habit plane variants, these layer cakes. You pick the one that has the most, and you allow it to break out into its two correspondent variant pairs. You're basically allowing one of the layers to grow at the expense of the other. And when you do that, and you predict the variant pairs that are going to arise because of detwinning, then we can match the high strain regions. It's the only possible way that we can match high strain. There was no other way to do it. There was no combination of variants that matched with a perfect habit plane that we could use that would explain what we were seeing experimentally. And for a long time, the community has been saying that you don't have detwinning before the end of the stress plateau. We came out with this and said we think you do, and then actually a guy at Colorado School of Mines came out with a diffraction experiment that also showed that, yeah, you're getting detwinning in the middle of the stress plateau. The reason this is important is because you don't have to yank it all the way up to superplasticity in order to get this type of detwinning. When you take this stent and you squeeze it, and you're in the middle of that stress plateau, you're actually causing detwinning, and this detwinning is linked very strongly to residual damage. So you're getting this very early. It causes residual damage in your stent. It hurts your stent. We need to consider it, and we need to figure out a way to knock it out so it happens later. We need to figure out a way so that when we squish the stent, we don't get detwinning, we don't get residual damage, and it'll just come right back. So these localized regions of detwinning are very strongly related to residual damage. And there's ways that we're looking at, okay, so how do you tailor the microstructure of these stents so that you don't get this damage? So that you can use these materials, you can torque them up through veins more strongly, you can be more rough on them to get them in a less invasive manner. You can bend them more. And I'm going to skip this because I want to go to learning. I want to make sure we have enough time. Okay. So how do you avoid this residual damage? How do you avoid this detwinning? Well, we have this very, very large data. So we've been able to look at a lot about this detwinning and know that this transformation does not change a lot of things in the modeling, where we know this transformation does not subsume an entire grain. It's very heterogeneous. You have a crosshatch pattern. The detwinning is strongly related to damage. The detwinning happens subgrain. It happens early. But how do you use that? So one of the things that we are working on is how to deal with this very big data that we're getting from our experiments. So you can imagine when we do this experiment, we take our sample and we pull it. And we basically get, in each experiment, 9 fields of view. And we get those 9 fields of view throughout the test as this specimen is being pulled. Each data point, in each field of view, we have 500,000 data points. So in each stop in the test, we have, 4.5 million? Okay? And then we have maybe 20 of those stops in a single test, and we do maybe 100 specimens. At each data point itself, so you can imagine it goes quickly up to hundreds of millions of data points. At each data point, we have an estimate of damage. That's the strain maps that you saw. You can see how much something has detwinned, right? At this point, x, y, we have this amount of residual damage and this amount of detwinning. So you have the damage map. That's why we broke out the mechanism, so we could get an estimate of damage. And then you also have, at each point, like 100 microstructural variables. So you can imagine, like, how close are you to grain boundary? Are you in a really big grain or a really small grain? How misoriented is the grain next to you? Just when you look, if I'm on the surface and I'm looking underneath me, do I have a bunch of small grains? Do I have a really big grain? What's going on subsurface? And so you have each data point, each of these hundreds of millions of data points that has an estimate of the damage map, but then also has 100 to 200 microstructural variables that's going on that explain the microstructure surrounding you. And what we want to do is look at how we know the microstructural landscape around you is really important, right? We showed that. It's not just the orientation of a grain, it's the local surrounding system, right? So what's bad about a local surrounding system that would cause you to have a lot of damage? Well, when we look at just the pictures, like I showed you, right, we couldn't find anything. So we're taking so many pictures, we have to use kind of these unbiased algorithms to pull out what's actually a pattern recognition of what's causing damage. So the way that we do it, that we're working on, and this is super new, is we take all our data. So we take this development of this methodology that we did with noise optimization, distortion corrections, nanoscale patterning, we get all this Ebsd data that tells us the microstructure. We can get a 3D reconstruction of what's going on through the specimen, whether it's by nano-CT or by polishing in Ebsd. And then we get many, many, many of these strain fields, where each one of these dots has an associated damage with it and the 200, 300 microstructural variables. And then we take this, and we characterize those 200, 300 microstructural variables as follows. So you have this reconstruction. You take a point right here, and you examine an area, a local area, that's kind of like a half sphere around that point. And the radius that you look at is probably going to depend on the strain at that point. We don't know, but we think it will, from some of the work that's coming out of CMU. And something even as simple as misorientation. That's how misoriented the grain is with respect to the grain next to it. If two grains are perfectly aligned, there wouldn't be a grain boundary. It can be in 4 different ways. So here's that microstructural field of view. For example, you can do something like how misoriented you are on average. So you take all the grains around you, around your grain, and you just say, oh, I'm 40% of my boundary is misoriented by this, 60% of my boundary is misoriented by this, this is my number. You can do it by volume. So instead of saying 40% of my area and 60% of my area, you can say that 40% that's really misoriented has a huge grain. So it's going to be a little bit harder to move, so I should count it more. And you can imagine kind of looking at the local misorientation in a half sphere too. So there's hundreds of these maps that we build that tell us characteristics, what's your grain size, how close are your grain boundary, different distance metrics to think about microstructure. And here's some examples. And then what we do is we take all of these, and you can imagine we put each value at a point on a slider. So I'm a data point. I have 200 different microstructural parameters, and I have a certain amount of damage at that point. Those microstructural parameters, I don't know which ones are important, but I run through, I put them each on a slider. You know, Schmidt factor is going to be really important. Misorientation is probably going to be important. Grain size might be important. And you basically run through different weightings to try to make, the idea being to try to make your microstructural clusters match where damage is inducing. And not point by point, but like, hey, 80% of the time, when I have a really big grain, and I have a lot of misorientation, and I have a small grain next to it, then I get this. So it's looking at these types of interactions between variables too. We're doing an approach that tries to not just look at like one variable in terms of grain size, but look at actually these, we're using hierarchical principal component analysis to look at interactions between variables. And then the basic tenet being that, that when you have nearby data points in the microstructural space, so you take your microstructural 100 to 200 variables, you dump them into 200 variable dimensional space, and you try to cluster them in that space. And we do that by neural net. So you just say, and you change the weighting, and you say, okay, these kind of belong together, these kind of belong together. You know, Schmidt factor is super important, so these are kind of clustered, these are clustered. And then the tenet that we use is that if you have points that are clustered in the microstructural variable space, they should match the clustering on average in the damage space. So we basically try to make these two maps match. And we do that by something called self-organized mapping. What self-organized mapping is a machine learning algorithm that basically takes multidimensional space and it brings it down to 2D. The damage one's really easy. I showed you guys those, right? I mean, that's a 2D space already. Red's really bad damage, blue's not. So that one's done. The microstructural one's tricky. So you take that data, throw it into 100-dimensional space, and you change the sliders, or the importance of each variable, until you get it to best match the damage map. And you do this for thousands and thousands of damage maps until you get a good match that occurs over and over and over again. The best match that you can find. And that starts to tell you which microstructural variables are important. The way that you cluster the microstructural data, the way that a self-organized map works, take the data points, throw it in 100-dimensional space, take a neural net, throw it on top, let the data points pull the neural net, and so that you have the best cluster possible. You're in charge of the sliders. You tell the neural net what are the most important microstructural factors. And you change those sliders so that you match your damage map. And you do that for thousands of fields of view. And it gives you basically a training data set that tells you, hey, these sliders seem to be really important. And then you try it on test data. So that's where we are right now. What we like about it is that it's completely unbiased. We have none of our bias in there at all. And what's coming out is actually when you do some, it's called HPCA, or hierarchical principal component analysis, all that does is it takes the factors you would put in, Schmidt factor, grain size, grain orientation, and it kind of combines them into fewer amounts of factors that are combinations of those. that it finds that are important. And so we do our self-organized map not in terms of the individual microstructural factors, but actually in terms of these combined factors. Problem with some of these machine learning, it's very new, and there's not a whole lot out there. One of the questions is like, how do you determine how big an area of microstructure you look at? Is it dependent on the local strain? Is it dependent on what microstructural feature you're looking at? Aspects of the surrounding microstructure, what's important. There's not a whole lot of information right now on quantifying like which distance metrics are good. There's a bunch of different ways that you can define distance. We're doing some clustering methods. You take those microstructural data, you cluster them around nodes, but there's limited evaluation of how good these clustering methods are. It's kind of a joke among the people who are trying to do this that you get a lot of pictures of cats. So when you look at clustering methods, it usually talks about like identifying pictures of cats for some reason. I don't like cats. And then when you filter, you actually lose some resolution. And then just the pure size of the data. We do not have the computational power to adjust sliders in every possible way. We have to very judiciously decide which ones we're going to look at to try to optimize our match. It does point us in the right direction. Like if you change this slider and it starts to give you a better match, you can tend to go in that direction, right? So there's some directionality to how you adjust this. I'm going to end there because I've gone a little bit over and I apologize. But this is my group. I just get to talk about it. They are awesome. I'm very lucky. And then obviously the funding that lets us do this work. And thank you guys so much for being such an attentive audience.
So we have time for a few questions.
When you do the electron microscopy images, do you know if the microscopy itself can contribute to what's going on in the mechanics?
If the
imaging technique, the fact that you're exposing it to an electron beam.
Oh, yeah, that's a really good question. We're pretty lucky. A lot of the metals and ceramics we look at are known to be pretty stable. If you were doing something like a biological material, absolutely. We do have some interaction between the microscope and the specimen in terms of like charging, and that contributes to drift distortion. So at small fields of view, drift distortion kills you at small fields of view. If your beam drifts in a big field of view, it's a less percentage than in a small field of view, so you just really see it in small fields of view. So it kind of sucks because spatial distortion will kill you at a big field of view, drift distortion will kill you at a small. So in small fields of view, when the specimen charges, it will actually change the drift, and we have to track that in time because the specimen is actually interacting with the microscope. But we're lucky. If we were doing biomaterials, it'd be something totally different.
I don't mean to misquote you, but halfway through, I think you said something that sounded fairly provocative. I think Miyazaki was wrong.
He was.
Right? And so what kind of reaction did when you published that? Did you get in the...
We were very lucky, so we published it. I don't know how else to I mean, I've been wrong. Like, people are wrong. That's experiment. You do the best you can, and I'm wrong sometimes. Like, everyone's wrong. And I wouldn't say, okay, so to be fair, saying that a single variant subsumes an entire grain is wrong. But there are uses in modeling where it's very useful. But you have to know the bounds on it. You can't use it for everything, and using it in mean field theory I don't think is appropriate. We were very lucky in that when we published this, somebody else at the exact same time published a theoretical calculation that also indicated that this was not a correct assumption. So it was just luck, but our experiments perfectly matched with their calculations. So it was nice to come out together. Yeah. I was very nervous reading that paper because I was like, because this is what we were seeing. I mean, yeah, it was wrong.
Other questions?
That strain is all from the phase transformation.
Okay,
so the phase transformation, when you do the tensile deformation in your release, anything that's reversible you can attribute to phase transformation.
Okay, so but you also have tensile deformation. So
yes.
You identify the strain. Whether this strain is from tensile deformation?
You're going to have some elastic strain, yeah. So you'll have a little bit of elastic strain. But when you release, so when you pull, that high strain, the great thing about nitinol is the high strain does relate back to the Martin-Cyclic transformation. When you release, you're going to have a residual strain. That residual strain is anything you recover has to be due to transformation and elasticity. Anything that remains has to be due to plasticity and locked-in Martensite. So it's combinations. It's very hard to decouple. You could probably do experiments in like diffraction to decouple them. We just know that everything that we pull with is going to be, if it's recovered, it's going to be transformation elasticity. If it remains, if it's residual, it's going to be plasticity and locked-in lines. Stuff that might be able to transfer back, but can't.
High strain has a fixed transformation, and the tensor strain at the same time. So how do you identify whether this is from tensor deformation or is from the fixed transformation? I mean, you do the tensor test.
Yeah.
And I mean, I have about 6% strain.
Yeah.
But this, I mean, you see a lot of strain. This strain can come from the phase transformation, or you can come.
The phase transformation accommodates the tensile deformation. So when you,
the same?
yes, they're the same. Yeah, yeah. Sorry to, yeah. So that all the all the tensile deformation, when you're pulling, the way that the specimen is accommodating that is by transforming. And it's really cool. I know it's weird because when you release, all of that goes back. Yeah. So they're the same.